Hello. In this video I will start to explain the twin paradox in Einstein's special theory of relativity. As I told you before, I will guide myself by Richard Miller's article published in 1971, which is unfortunately not freely available online. What I find interesting in this article is that he analyzes the twin paradox from the traveling twin's point of view, namely from a non-inertial system's point of view. The motivation for these videos on the twin paradox is that I've often seen physics students waste a lot of time on this, trying to understand it and not really grasping the concepts behind the special theory of relativity very well. Now, going back to the Lorentz equations, which are these here, you should realize that lengths will appear contracted from the point of view of an observer at rest, looking at the moving system. So let's take two observers, a blue observer and a black observer. The blue observer is moving with velocity v, and the black observer is stationary at rest. And if you take a stick of 1 meter, represented in blue here, at rest in the prime system, you will have delta x prime is equal to 1 meter. So that's what the blue observer measures, 1 meter. For comparison, and say that the fixed observer, represented in black here, keeps an identical stick that is black in his system, and because the physics is the same in both systems, the lengths of identical sticks is also the same. So this black stick measured by the black observer is also 1 meter. Now, let's look from the point of view of the black observer. The black observer is trying to measure the blue stick, so the moving stick. In order to do that, of course, he takes both ends here to be at the same time in his system, so delta t is equal 0, because the black observer measures both ends of the stick at the same time. And plugging this into the second Lorentz equation here, he will get delta x is equal to delta x prime divided by gamma. So what he sees is that the blue stick is actually less than 1 meter from his point of view, and this is called the Lorentz contraction. Just to have fun with it, the only way for this contraction to happen is if the left end of this stick appears to the black observer, that it starts to move first, and the right end starts to move last. So when you want to accelerate a rocket from rest, for instance, you cannot accelerate each point at the same time, or it will break. Now conversely, to the blue observer, watching the black stick, it will look shorter as it's starting to move relative to the blue observer instantaneously. By the way, in these slides I always consider that the moving system accelerates instantaneously with velocity v in order to simplify the analysis. Alright, moving on. Now let's ask ourselves what happens to time. We saw what happens to length. And let's assume we have a stationary observer, again represented in black, who has 3 clocks at 3 different positions. And now the blue observer has a blue clock which is initially at rest. Then the blue observer, who is initially at rest at t equals 0, will step onto a rocket, so moving at velocity v, and accelerate instantaneously at velocity v. One thing that is usually not mentioned in textbooks is that as this the blue observer accelerates and changes his reference system, his personal clock doesn't suffer any discontinuous jumps in its reading, assuming of course that the construction of the clock is rugged and it doesn't get affected by the sudden acceleration. So if the blue clock showed 0 just before the acceleration, it will also show 0 time, t prime equals 0, after the instantaneous acceleration of the blue observer. Alright, now moving to the next set of cartoons. To the stationary observer, to the black observer, the blue clock will also appear to show 0 time just after the blue observer has accelerated to velocity v. This is because of the principle of simultaneity. We have two inertial systems traveling at speed 0 and at speed v, and two events with no spatial separation, which is the click of the blue clock when it reaches 0 indication on its dial, and the sudden acceleration of the rocket at x equals 0. So these two events are separated by delta t prime is equal 0 in the frame of the moving observer, and by delta x equals 0 because they happen at x equals 0, and thus they are separated by delta t equals 0 in the frame of the black observer. Thus, just after the sudden acceleration, the blue clock will appear to show 0 time still to the black observer. So, to a black observer situated at some x position from the blue clock's reading doesn't suffer any sudden jumps when it accelerates suddenly. Alright, now moving to the last set of cartoons. First of all, to the blue observer, the black clocks will seem to be closer together than to the black observer. And this is due to the length contraction that I told you about. But what about the time reading? According to the equations, to the Lorentz equations, if we go back to the Lorentz equations, going to these equations, t prime will get more and more negative towards the right because t is 0, so t prime is just gamma minus vx over c squared. So t prime gets more and more negative towards the right. That means that in the moving system, the black clocks strike 0 at negative t prime. That means that at t prime equals 0, they have already struck 0 time in the past, and thus their current indication is positive time and growing towards the right. So, from the point of view of the blue observer who suddenly accelerates, the black clocks situated further and further away will suffer a bigger and bigger sudden jump in their reading. This is quite different from what the stationary observer, the black observer, observes, who is in an inertial system. Because for the observer in the inertial system, looking at the blue clock, so here the observer, let's say at this point, looking at the blue clock, which suddenly accelerates to velocity v, there doesn't appear to be any sudden jump in the reading of the blue clock. Now, if you think in terms of the relativity of simultaneity, the two black clocks here appear to strike 0 time simultaneously in the stationary system, and however, as seen from the blue system, seen by the blue observer, they do not strike 0 simultaneously. And I will start talking about the twin paradox and continue in the next video. In the twin paradox, you have two twins, which Richard Muller is calling them John and Mary, and applying the Lorentz equations from John's point of view, who is at rest, we'll have this equation. Subscripts m and j stand for Mary and John. This equation is for half of the journey, so when Mary reaches the turning point is where the first half of the journey ends. At that point, the distance traveled that's seen by John is given by this equation, and plugging this into the first equation you get this. Now John is in an inertial system, and as we have seen, for him that means as he looks at Mary's clock, he doesn't see any sudden jumps in the reading of Mary's clock. So because of that, the t prime that Mary measures you can consider is also the time that John measures on Mary's clock. So in this formula, TM is both the time that Mary reads on her clock and the time that John reads on Mary's clock when he looks at Mary's clock. It looks like Mary has aged less than John during the round trip. And this is so because the same equation holds on the way back, and using exactly the same arguments, you'll get exactly the same equation. Remember, this is from John's point of view. From John's point of view, there are no sudden jumps in the readings of any clocks. Thank you for watching this video, and in the next video I will discuss this paradox from the point of view of Mary, who is in a non-inertial system.